everybody. I want to talk to you about some work that was done primarily by my former student, Anupam Das, who's just finished up his postdoc at CMU and will be starting as an assistant professor at NC State in the fall. If any of you know of promising graduate students, send them his way. Also with Edward Chu, who was an undergrad at the University of Illinois, and he's since moved on to be a grad student at Stanford. So we've heard a lot about tracking already in this conference. And one of the things that's been happening in recent years is users are increasingly turning to various types of tools to try to limit the people's ability to track them. So Privacy Badger, Disconnect, Ghostery are extensions that keep growing in popularity. And we've even seen these things move into the mainstream. So Brave, they had a bunch of stickers over there. I got one. That is a browser that's specifically designed for privacy and tries to prevent various types of tracking. Firefox Focus is another privacy-focused browser. And then, of course, Apple announced that their new version of Safari will incorporate tracking protection by default. The tracking and advertising industry has not been taking this lying down. They have, in particular, spent a bunch of time trying to figure out how they can track people through other mechanisms than the traditional cookies. So, for example, in 2012, Maori and Shacham developed this fingerprinting technique where you can render text and use this rendered image as a fingerprint to try to distinguish different devices based on their operating system, fonts, and so forth. And in 2014, it was found that over 5% of the top 100K Alexa sites were actually using this fingerprint to try to track users. So today, I want to talk about tracking in the mobile browsing context. One of the things that happens is that if you try to fingerprint mobile users using traditional techniques, such as canvas fingerprinting, browser fingerprinting, and so forth, you actually have somewhat less ability to do so, especially in the Apple side of the infrastructure. Apple has relatively homogeneous hardware platforms. They have very fast upgrades in the sense that a very large percentage of the user population upgrades to the latest version. There's more limited ability to customize your browser with fonts and extensions. And in fact, this was documented in a couple of papers that mobile fingerprinting doesn't work as well. On the flip side, mobile browsers have a bunch of sensors that are embedded in them and that are available to websites. Not all of these are available to websites, so we particularly focus on motion sensors. So motion sensors are ones that are accessed through the Device Motion API. This is a standard API implemented by all mobile browsers. If you want to check it out, you can actually just go to this URL if you have a smartphone. I won't mind. I won't be offended. And this API provides access to the accelerometer and the gyroscope. And most modern smartphones have both. Some cheaper, older smartphones just have the accelerometer. One interesting thing that you'll see if you try this is that this API is available to any web page that you connect to over your mobile browser without any authorization. There's no permissions, nothing. And so if you go to this site that we set up for you, in this site you are able to, we show you the accelerometer values that you have. But of course, that's just because we try to make it visible. It is very easy to collect these sensor values in the background and do anything with them. And those of you who did try this web page, you might notice that even if you leave your phone stationary somewhere on a desk, these values keep jumping around. There's a bunch of noise that happens among the readings that you get from these values that comes from various physical and environmental factors. So the question that we're looking at is, can you use these readings, essentially the noise that is created by the accelerometer readings, to identify individual devices through the application of machine learning. So our workflow is basically we take training traces that are collected just by taking them through the device motion API. We extract some features through it through basic signal processing, something like mean, variance, the power of the signal, and so forth. We then put them to develop a classifier using supervised learning, so we know which device generated which trace. And then we can take a test trace and try to classify it. So this is the overall approach that we're taking. In fact, this is the approach that's been taken by a few different research studies with various results. So we had a paper a couple of years back that did this on kind of a smallish lab study that showed that we had pretty promising results for being able to fingerprint motion sensors. One of the things that we wanted to do in this paper is really dive into the understanding how well this would work in a real-world setting. So the first thing that we did is we worked with a much larger data set than previous studies, and we also wanted to test the environment in a much more realistic scenario. This led us to then need to improve the algorithms that we had used before to adjust them to use more types of data. We developed a special voting algorithm to improve the classification accuracy and to adjust them to an open world scenario. And then finally, what we did is we looked at developing defenses for this kind of fingerprinting. So let's start with our initial study. So we recruited users through an email survey and by sending out paying people through Mechanical Turk. We collected, each user would use their own personal smartphone to go to a web page that we set up, and that would allow us to collect a bunch of samples of their accelerometer readings in two settings, so the phone being on a desk and the phone being held in their hand. And we got 294 users' traces in the on-desk scenario and 256 in the in-hand scenario. We tried a few different classifiers to work with the features that we had, and we were able to get pretty good results. So we had, out of the 300 users or so, we had 86% accuracy in the desk scenario, and not quite as good in the in-hand scenario. But it turns out the results were a little too good. So this was the way that we were first analyzing the data. We had the users collect 5 samples with a phone in their hand. Then we had to put them down on the desk, and they collected 5 samples on the desk. We had to then pick it up again, collect 5 more samples, and put them back on the desk. And then when we evaluate, say, the in-hand scenario, we take the 10 in-hand samples, we randomly split them between the training and testing set, and we evaluate the accuracy of our classifier. When we tried an alternate approach where we used the traces from the first so-called session, the first 5 samples for training, and the second 5 samples for testing. And turns out that our accuracy dropped significantly. And this was a very interesting result because it highlights some of the difficulty in trying to evaluate these kind of attacks, especially in the lab setting. There's a number of studies that try to look at including ours, that look at accelerometers in the lab. And so the question is, are they picking up kind of very transient fingerprint properties where maybe just the way you place the phone on the desk creates an effect that you can observe? Or are they picking up something that's more inherent to the phone? So working with this new experiment design, we spent some time trying to improve the fingerprinting accuracy. So we used a bunch of new features. We had some processing to extract not just the raw X, Y, and Z values for the gyroscope, but also the azimuth and inclination to kind of show the position that you hold. Also looked at acceleration without gravity to try to factor out the large magnitude of acceleration that might have been confusing in machine learning algorithms. And then we developed a special voting-based classifier that boosts the accuracy of our classification. You can find the details of this in the paper, but the long and short of it is that we're able to get 73% accuracy on about 300 people in an on-desk scenario and 60% in an in-hand scenario. So what does this mean? Does this mean that fingerprinting works, fingerprinting doesn't work? Well, 73% accuracy probably isn't all that great all by itself, right? You aren't able to, in a quarter of the cases, you're getting the wrong person identified. But you can actually do some quick back-of-the-envelope calculation and say that if you think about information-wise, we're getting at least about 4 bits of information in hand and 5 bits of information in the on-desk scenario out of this. So then the question is, if you are getting some useful information out of the sensor fingerprinting, and the question is, can you combine this with enough other features that you can extract, such as maybe the user agent, maybe somebody's network location, and so forth, to be able to classify them. And we have in the paper some discussion that looks at some scenarios and how well this works and how well this doesn't work. In the interest of time, I'm going to skip past that and talk to you about some work that we did in the mitigation side. In the mitigation, we did 2 approaches. One is that we obfuscated the signal by adding some noise to the sensor readings. The noise actually has to be correlated so that you aren't able to just remove it by signal processing, though you have to change it across sessions. And there's more details about that I can explain later. And then the second approach that we tried is very simple, where we just quantize the readings. We essentially can think about dropping readings past a certain, dropping all the numbers after a certain decimal, or quantizing them into certain sized bins. And so you can see in the graph here that this does significantly reduce our ability to fingerprint smartphones. But the question we want to look at is, how does this impact people's ability to use the accelerometer in application? And so we try to figure out what people use this for, and we thought one of the more demanding applications of accelerometers is actually playing, kind of a tilt-based game. So we built one that we had users play. It's a game, in fact, if you really want, after the talk, please, we can go to this URL and you can try this game on your own phone and see how you like it. What we had is we had users play this game in a normal setting where they were getting the raw accelerometer data, in an obfuscated setting where we added noise to the data, and in a quantized setting where we removed the last few bits from the data. We didn't tell the users which setting they were on, and we randomized them. And then we asked them how easy it was to control the phone for a subjective metric. We also measured how fast they were able to complete each level. And there's details about various analyses that we did of the results in the paper again, but the TLDR of it is that there was, with a study with 400 users, we found no statistically significant differences in either the objective or subjective metrics. So there was not an impact that we could see from applying this countermeasure. So in conclusion, our results of our work are a little bit nuanced. We showed that as compared to some previous work, the ability of applying sensor fingerprints in the real world is more complicated. It's more difficult to get useful results. On the other hand, there's still useful information that trackers could extract from these kind of sensor fingerprints. And we showed that you should be able to mitigate these attacks significantly with a minimal utility loss. One last thing I want to point out is that we have a paper that was just accepted into CCS where we show that not only could they be, but people are in fact using accelerometer data in conjunction with fingerprinting scripts already. So we will present that in Toronto in a few months. Watch this space. And if you're interested in seeing our data or playing this game, you can go to this URL, This will be a permanent URL. The short URLs will disappear in a couple days. And I'd be happy to take some questions.
Hello. Thanks for a good talk. Just about the classification problem. So, if I understand it correctly, you have a separate class for each of the 294 users, or
a separate, sorry?
A separate class for each of the 294 users.
Separate task?
Yeah. So, separate class for each of the 294 users. If you want to test if to track users, you have your classifier. What is the positive class in that case?
I'm not hearing the word. Was it a separate?
Class.
Class.
Yeah.
Yes, I have a separate class for each of those 294 users. What was the second part?
And so, how would you then measure the accuracy of the classification? If
the accuracy is just the average accuracy. So the percentage of time you could say for each user, what percentage of the time did they get classified into the correct class, and then you can average it over 294.
Hey. Two questions. First one, how much difference does the sample rate make to the accuracy?
Can you speak up a little bit? Just a little earlier.
How much difference does the sample rate make to the accuracy of...
We did some analysis of this in our previous paper in CCS 16. The sample rate does have some impact. It's not a dramatic difference.
And second question related to that. If you use the native APIs rather than the browser APIs, do you think it would be more accurate? Because I believe that the browser actually rate limits the
yeah, it's a good question. The native API does sometimes support a higher sampling accuracy. We have not done this study because our focus was, especially in this paper, was in fingerprinting in the context of web pages fingerprinting you rather than devices doing this. But that's an interesting question. Unfortunately, our data collection methodology doesn't allow us to use the native API because we just ask people to use the web page, but maybe some lab study could be an interesting follow-up.
Yeah, about the mitigation strategy. Would that have an impact on applications such as maps or running applications if the error kind of compounds over time, or do these applications correct with the new GPS and it wouldn't be?
That's a good question. You can get closer to the mic. Okay. That's a good question. If you were in running applications, sometimes you do step detection, and I'm trying to remember. I'll have to answer it offline. We had one test with step detection, but I don't remember the results.
So we have time for one more question. Okay.
Hi, thanks. I'm wondering whether the mitigation of dropping digits is effective enough, and can you still fingerprint users based on kind of how they use their phones, like on the behavioral stuff? I don't know, like how this mitigation, how effective this mitigation is.
Are you asking how good the mitigation is? How we can evaluate that, or?
Sorry?
Are you asking about the quality of the mitigation?
Sorry, I'm wondering how good the mitigation is of just cutting the precision of the values. Can you still fingerprint users if you do this kind of mitigation? Like how effective it will be?
Our main finding is that you're still able to get some better than random fingerprinting of people, but you get significantly less information. I haven't computed the information content of that, but actually I can do that pretty quickly and get back to you.
Okay, thanks.
Thank you.
I have one final question. Can you provide some spoilers about which companies are doing this in the wild?
Which what?
The companies using that sort of fingerprinting technique in the wild?
Oh, which companies are
Yes.
doing this? Let me just
If
keep
you can.
people in suspense until we put our CCS papers out. I think one thing I can say is that we noticed that, among other things, companies that are trying to do bot detection, that try to analyze whether the click came from a real person or a bot, are among the people doing this.
Thank you. Let's thank Nikita for.